Okay, so our new topic is iterative methods. So remember that we use Gauss elimination for the solution of linear set of equations, and the CPU time exponentially increases with the number of equations. Therefore, we prefer to use iterative techniques, some approximate techniques for the solution of large linear set of equations. Again, we have coefficients which we want to determine which comes from the problem flow. So here the A's are the coefficients, again X values are the unknowns, and B's are the right hand side of our equations. So we have n unknowns and n equations, as is the case in Gauss elimination method. Now our first approach is Gauss-Jacobi method, and it is much more better if we explain it by using a graphical approach. So just assume that we have two equations with two unknowns, and let's give a number to them. Let's say that this is our first equation, and this is our second equation. We can give different numbers also. So what we do in Gauss-Jacobi method is we begin with the approximate values of x1 and x2. So remember that if you make an approximation, for example, for the first equation, if you make an approximation for x2, you can calculate the x1 from this equation easily. And it is the same for the second equation. If you make an approximation for x1, you can use calculate the value of x2 from the second equation. And this is why you do how you do it. So you give number to each equation, and then you calculate the corresponding unknown from that equation, and you substitute for the next step. You use new approximations, because you have now new approximations from these equations. You substitute these new values in the second step, and it goes like this. So let's see how it works. So we have an approximation for x1 and x2. So let's say that our first approximation for the x2 is 6. When you substitute 6 into this equation, you got 12. And then from here, so you substitute the 6 into this equation, and you approximate the new value for x1. So that is 2. So 2 is my new approximation for x1. Now let's have another approximation for x1, because 6 is my first approximation for x2 in my first iteration. Therefore, I need another approximation for x1 in my first iteration. And let's say that that is 3. So I substitute 3 into the equation 2. So this gives me -3. If I put it here, I got 2.5. For the new value of x2. Now I have two new values. For x2 it is 2.5. And for x1 I have 2. Now the point is this: I will use this 2.5 value in calculating my new x1. and I will substitute it into the new equation. If I substitute 2.5 here, this makes 5, and there is 13. 13 divided by 3 makes 4.3 approximately. So it goes here, and then it goes here. Now let's focus on the value of the 2. Now I will use 2 for calculating the new value of x2. So yes, so this is my new approximation for x1. I substitute x1 here as 2, so it goes therefore 4 divided by 2, it goes to 2. And it goes like this. As a result, I have new approximation for two, and I have new approximation for x1. So from the first iteration to the second iteration, I go from 2.5 to 2, and from here I go from 2 to 4. So it goes like this, and you continue to do it successively. So this is the basis of the Gauss-Jacobi method. So how is the formulation then? So we have approximation for all the unknowns and we take out one of the unknowns and make a better approximation for it by using the values of the rest, simply. So we substitute into our equation all the approximations. So for example, in the first for the first equation, you substitute the approximated values for x2, x3, and xn, for example, and you calculate a new value for the x1 by using this expression. Then you do the same thing for x2. You submit the values for x1, x3, and xn, and then now you have a value. From here you can easily calculate the x2. Therefore, x1 and x2 are better approximations. So x1 I plus 1, x2 I plus 1, and then it goes like this: xn I plus 1. You have a new approximation for all the unknowns. Now for the next iteration, you use these values and you continue to do it iteratively until your relative approximate error decreases below a certain value. This is the base. This is the Gauss-Jacobi method. Of course, we can further improve the technique. Now we reach to Gauss-Seidel. So how the Gauss-Seidel method works? Again, we begin with some initial guesses for the unknown values, unknown variables. And then we give numbers to the equations. Of course, from there, for example, for the first unknown, I can calculate the x1 I plus 1. Now, for the in calculating the value or approximate value of the x2, what I do is, now I have a better approximation of x1 I plus 1. Therefore, I use this approximation in order to have a better, more accurate approximation for the x2 I plus 1. And it goes like this for the rest of the equations. Of course, the number of iterations for the Gauss-Seidel method is smaller than the Gauss-Jacobi method because you are using a better approximations for the unknown variables in Gauss-Seidel. So let's see how Gauss-Seidel method works graphically. Again, you have two equations with two unknowns, let's say that. And then you begin, just think that hypothetically, you begin from a certain point, and then you go to the next. You put a value here, and this basically means that by using this new iteration, you calculate the second unknown, and then you substitute this value into the second equation, and then you calculate the better approximation for the first variable. Then again you go like this. At the end you reach to the solution. Now, of course, this doesn't guarantee the convergence. In some cases, it's probable that you choose the other equation for the as the first one, and let's see what happens then. Look, you go here, and then you go to the second equation, then you approximate the x1 from here, you substitute this x1 into the first equation, and then as you see, you are getting far away from the solution, so you are diverging from the solution. This basically means that, so how to avoid it? Now, your coefficient matrix must be diagonal dominant. What it means? Now let's return back to our set of equations. As you see, we divide all the right-hand side to the coefficient of the unknown variable. For example, here it is A11. Now, in order to guarantee the convergence, sum of the coefficients of the rest of the variables in that equation, so A11 plus A1, absolute value of the A11 plus A13, A1n has to be smaller than A11. This guarantees the convergence in Gauss-Seidel method. Okay. So this is how the Gauss-Seidel method works. Again, if depending on the problem, sometimes we want to decrease the number of iterations, or sometimes we want to guarantee the convergence. We need to improve this. Again, in order to achieve a solution with the Gauss elimination, Gauss-Seidel or Gauss-Jacobi method, certainly your coefficient matrix must be invertible, and it has to be well conditioned. So the condition number has to be at an order of 1. Now the point is this. For the well-conditioned problems, sometimes we want to arrive the solution in a much more faster way. So we want to decrease the number of iterations in order to decrease the CPU time. How we do it? Then we use relaxation, or maybe the coefficient matrix is not diagonal dominant, it's probable, and you want to achieve a convergence at the cost of CPU time, then you use under relaxation. So what is under relaxation and what is over relaxation, or in general, what is relaxation? So remember that we have two values for the approximation. One is the coming from the previous iteration and one is from the new iteration. Now we can combine them in a linear fashion and we can form a new approximation. How we do it? We multiply the value that we have calculated from the new iteration with the lambda. Lambda is a parameter that's called under relaxation parameter. Sorry, it's a relaxation parameter, not the under relaxation. So this is a relaxation parameter. Lambda is the relaxation parameter now. And the point is this: we use new value by using the lambda. Now lambda can be chosen in different ways. If you choose the lambda between 0 and 1, this is called under relaxation, successive under relaxation. So certainly your value for the next iteration will be between the new one and the previous one, when lambda is between 0 and 1. This is called successive under relaxation. This is generally what we prefer if the coefficient matrix is not diagonal dominant. So basically this operation under relaxation grows the increase the value of A11 in an artificial way. But if the matrix is highly diagonal dominant or it's well conditioned and you want to decrease the number of coefficients, number of iterations, then you use over relaxation. In that case, what you do is you choose a lambda greater than 1. Now choosing the lambda greater than 1 will tell you that basically you are approaching the solution from the right way. And the new value, or let's say that the value for the next iteration, so let's say that delta x here, x new and x old, the difference between the x new and x old gives you the delta, so the change in the variable. So choosing a lambda greater than 1 means that you multiply that delta value, so the relative change, multiplying that delta with the lambda, and choosing a lambda greater than 1 will tell you that, okay, so get a larger delta and sum it with the previous iteration value that comes from the previous iteration. In fact, this means that you basically think that you are in the right direction in the solution and you want to reach to the solution in a much more faster way. This basically tells you that, okay, the number of iterations, you will have less number of iterations. In this case, this basically means that you have lower CPU time. So this is how the relaxation is used. So if lambda is between 0 and 1, it is under relaxation. If lambda is greater than 1, it's over relaxation, and generally lambda is chosen to be for over relaxation between 1 and 2. You can use larger values for the lambda. I mean, you can use larger values than 2, but this may cause divergence. What else? Now, in some physical problems, many of the coefficients are 0. And generally, we see that if the problem is well organized, coefficients lies only along certain lines in the coefficient matrix. These matrices are called banded matrices. So only certain terms away from the diagonal are non-zero, and the rest is 0. Rest of the terms, rest of the coefficients are 0. We have the diagonal of the matrix. Now, the distance between the first coefficient and the last coefficient is called bandwidth. Okay. Now, the thing is this. Certainly, the distance between the diagonal to the last coefficient is half bandwidth. So this is these are the things. This has some advantages. Certainly, you can easily store only the non-zero elements, non-zero members of the coefficient matrix, and this will significantly decrease the memory, allocated memory, especially when you are dealing with the large matrices. One banded matrix is called three-diagonal matrix. So let's say that we have a system of linear equations. Here, this matrix is the coefficient matrix. X's are the unknowns, and R's are the right-hand side of our equations. The diagonal terms are represented by F, and the terms above the diagonal is called G, and the terms below the diagonal are represented by E, letter E. As you see, in order to define the coefficient matrix, I only need to define 3 arrays because the rest of the terms are 0. So these terms are 0. In this case, we can use some special techniques. One approach is the Thomas algorithm. So remember how we use the Gauss elimination. First step is the decomposition. So we basically decompose the matrix in the upper and lower part. Lower and upper part, and this is the decomposition step. Here the Poseidon code for the decomposition step. So EK is divided by EK divided by FK minus 1. So you divide E2 with FK minus 1, and then you update the FK, so F2, by F2 minus E2 multiplied by G1. So as a result, you have the lower diagonal with the diagonal terms 1, and then you have the upper diagonal matrix with the new diagonal terms. So the G's are there. Now the situation is rather straightforward in this case. You can easily solve such a system because taking an inverse of a lower diagonal is quite straightforward. First, you apply forward substitution, and then you calculate the variables, new variables, let's say rk, that is rk is equal to rk minus ek multiplied by rk minus 1. So you are left with the upper diagonal matrix and unknown terms. So you can think like this. Now you have an upper triangular matrix. As a result, you can easily apply the back substitution by using this these operations. So you have an approximation, you calculate the xn, and then you continue to do the back substitution. Of course, Thomas algorithm will give you the exact solution of the problem, linear set of equations. This is significantly advantageous. Let's look at the number of iterations. You do n-1 iteration here, you do n iteration here, and you do again n-1 iteration here. And just look at the number of floating operations. So here you have one division, one multiplication, and one subtraction. So you have 3 iterations here. You have 3 multiplied by n-1 here. You have 2 multiplied by n-1 here. So it makes 5 multiplied by n-1. And let's look at the number of operations here. So one multiplication, one subtraction, and division. So you have 3. In total, you make 8 times n-1 floating point operations. This is significantly lower than the Gauss elimination method. This is a technique that can be used for solving the linear set of equations with 3-diagonal coefficient matrix. Certainly there are other iterative techniques which can be used and which significantly improves the convergence and solution of some linear set of equations, including the ill-conditioned problems. You can just take a look at the internet and find the algorithms for these techniques. So one is the conjugate gradient method, which is widely used and quite simple and straightforward. Conjugate gradient stabilized methods, biconjugate gradient method, biconjugate gradient stabilized method, minimal residual, and gradient minimal residual method. So these are the other iterative techniques. Certainly you can use under relaxation or over relaxation with these iterative techniques. Just have a look at the internet or books on numerical analysis.